On March 26, 2024, the container ship Dali lost propulsion and drifted into the Francis Scott Key Bridge in Baltimore, collapsing the span in seconds. Many dismiss it as a fluke, a freak accident caused by bad luck or pilot error, but data reveals over 30 major bridge ship allisions in 50 years, each with similar root causes. This is Wings and Wrecks, how machines fail and what saves the people inside them. The common belief is that bridge ship collisions are rare flukes, caused by pilot error or bad weather. But the data tells a different story. According to a 2018 Piank study, approximately 1 in 10 bridge ship allisions results in collapse. That is not a fluke, it is a systemic failure. Over the past 4 decades, at least 10 major bridges have collapsed due to ship impact, killing hundreds. So why do giant ships keep hitting bridges? The answer lies not in a single cause, but in a chain of failures. The pilot's impossible job, the wind on high-freeboard ships, and propulsion loss at the worst moments. This is not a story of blame, it is a story of systems. What do you call it when a moving ship strikes a stationary object like a bridge? Maritime law defines this as an allision, not a collision. The distinction matters because it shifts the question from who was at fault to why the ship could not stop. So why did nobody stop the Dali before it struck Baltimore's Francis Scott Key Bridge on March 26, 2024? The ship had lost propulsion and steering just minutes before impact, leaving the pilot with no means to avoid the bridge, according to the NTSB. But this was not a random fluke. The Dali's power blackout was a known risk for modern ships with complex electrical systems. And the bridge, built in 1977, had no protective dolphins or fenders around its main piers, a vulnerability shared by many older spans worldwide. 3 key factors converged that night: pilotage in a confined channel, wind pushing the high-freeboard hull, and sudden propulsion loss. Each one alone might have been manageable. Together, they turned a routine departure into a catastrophe. So why did nobody stop it? Because the pilot, the person steering the ship, was already fighting forces that no human alone can control. In a confined channel, a ship's momentum is measured in thousands of tons, and the margin for error is measured in feet. A pilot has only seconds to react when propulsion fails, and even the most experienced cannot overcome physics. On May 9, 1980, the freighter MV Summit Venture was approaching the Sunshine Skyway Bridge in Tampa Bay when a sudden squall struck. Visibility dropped to 0. The pilot, with decades of experience, lost all reference points. The ship veered off course and slammed into a support pier. The pilot did everything possible, but the ship was at the mercy of the wind and current. That statement from the pilots' union after the 1980 Sunshine Skyway disaster captures a bitter truth. In these moments, the pilot is not the cause, but the last line of defense. And when that line is breached, the outcome is catastrophic. Today, modern container ships rise 50 meters above the water, their vast sides catching wind like sails. In a narrow channel, a sudden gust can push the ship sideways faster than the pilot can correct. The margin for error in these channels is measured in feet, not miles. A modern container ship's hull rises 50 meters above the waterline, a vast vertical wall that catches the wind like a square rigger in a gale. In a narrow channel, that wind becomes a force the pilot cannot counter, pushing the vessel sideways faster than corrections can compensate. The numbers confirm it. Lloyd's register data shows that a ship with a freeboard of 50 meters experiences a lateral wind force of over 100 tons in a 20-knot breeze. That is enough to push the vessel sideways at a critical moment, especially when the channel is only a few hundred meters wide. That is exactly what happened on the Mississippi River in 2012. The towboat Delta Mariner lost engine power while approaching the Vicksburg Bridge. Without propulsion, the wind took control, pushing the vessel into the bridge pier. The damage was minor, but the lesson was clear. Wind is a pilot's invisible adversary. So why did the Dali lose power at the worst possible moment? The answer lies in the ship's electrical architecture, a complex system vulnerable to a single point of failure. On many modern vessels, a momentary blackout can cascade, leaving the pilot helpless with no means to avoid the bridge. This is not an isolated case. In 2012, the towboat Delta Mariner suffered an engine failure while approaching the Vicksburg Bridge. The crew lost all propulsion and steering, drifting into the bridge's protective fender system. The damage was minor, but the pattern was clear. A review of major bridge ship allisions over the past 4 decades reveals that propulsion loss is a factor in nearly half of all cases. The data from PIANC shows that mechanical failure, not human error, is the common denominator. The problem is that modern ships rely on complex electrical systems that can fail without warning. A single faulty breaker or a momentary voltage dip can trigger a blackout. And when it happens in a narrow channel, there is no room to recover. The Francis Scott Key Bridge, built in 1977, had no protective dolphins or fenders around its main piers, a vulnerability shared by many older spans worldwide. According to PIANC, over 60% of major bridges built before 1990 lack adequate ship impact protection. Protective dolphins are the first line of defense, but many older bridges lack them entirely. According to PIANC guidelines, such systems can reduce allision forces by up to 80%. Without them, a ship's kinetic energy is transferred directly to the pier. And that is exactly why the 1993 Big Bayou canot-to-rail bridge collapse was so tragic. A towboat lost its way in fog and struck the bridge, knocking it out of alignment. Minutes later, an Amtrak train derailed into the water, killing 47 people. The bridge had no protection at all. The lesson is clear. Armour matters. PIANC data shows that protective dolphins can absorb the impact of a drifting vessel, giving the crew time to regain control. But retrofitting every vulnerable bridge is expensive, and many remain exposed, waiting for the next ship that cannot stop. So what happens when a ship with no steering meets a bridge with no armour? The answer is physics. A vessel the size of the Dali, moving at 8 knots, carries kinetic energy equivalent to 1.5 gigajoules, enough to lift a fully loaded Boeing 747 100 feet into the air. That energy has to go somewhere. Most bridge piers are designed to withstand a glancing blow, not a direct hit from a ship that has lost all control. When a pier fails, the span above it collapses. And that is why these events are not rare flukes. They are the predictable outcome of a system where a single point of failure can release enough force to bring down a bridge. So what can be done? The answer lies in 3 areas: bridge protection, propulsion redundancy, and pilot training. Retrofitting older spans with protective dolphins can absorb impact forces, but the cost is high and many remain vulnerable. But even the best pilot cannot simulate a blackout in a simulator, because most simulators do not include sudden power loss scenarios. The Dali's pilot had no way to practice that exact failure. This gap in training leaves pilots unprepared for the most critical moments. So why not add backup systems? Because redundancy costs money. A second generator and separate electrical bus add millions to a ship's price. Many shipping lines choose to save that cost, betting that a blackout will never happen in a critical moment. That bet is increasingly risky. Wind forces on high-freeboard ships are so critical that naval architects now use wind tunnel tests to predict how a vessel will behave in gusts. These tests reveal that even a 10-knot crosswind can push a container ship sideways by several ship lengths in a minute. And the channel itself is part of the problem. Many major bridges were built before today's megaships existed. The channel width under the Key Bridge was only 700 feet, less than 3 ship lengths. That leaves no room for error when a ship drifts. Retrofitting a bridge with protective dolphins costs tens of millions of dollars. For the Key Bridge, the cost was estimated at $50 million, a sum that was never allocated. After the collapse, the economic impact reached billions, dwarfing the cost of prevention. After the 1980 Sunshine Skyway collapse, new bridges in Florida now include massive concrete islands around their piers. But many older bridges remain unprotected. The lesson is clear. We know how to prevent these disasters, but we choose not to pay for it. But the most important lesson is this: these disasters are not rare flukes. They are predictable systems failures. Understanding the chain of events, pilotage, wind, propulsion loss, is the first step to preventing the next allision. If you want to know why machines break and how crews fight back, subscribe. Next up, our next video.